Hi, welcome back in your journey here in Unit 4 of Linear Momentum. So in the last video, we wrapped up the impulse momentum part of this chapter, which are the first two topics. And then the final two topics are going to be conservation momentum. And so momentum is a conservation law, okay? And so one thing that you may have to do is check the velocity of the center of mass, because the center of mass, again, will play a very important role here. So a collection of objects with individual momentum can be described as one system with one center of mass velocity. And then for a collection of objects, the velocity of center of mass is given by the equation of V sub Cm is the sum of Mi Vi over total mass. Okay. And what you could see here, there's M times V. Well, that's momentum, right? So this velocity of the center of mass does go back to the momentum of the object or the system, okay? Conservation of momentum states, in the absence of net external forces, the total momentum for a system is constant. Now, if you recognize that a free response question is a conservation momentum question, make sure you write something down that says that this is conservation momentum. One way to do it is to say, in fact, so the delta P of the system is equal to 0. Well, what does that mean? The momentum of the system is constant. So you have to take all of those individual objects and find the total momentum of the system. And now what happens is that, each side equals each other in this case. Another way to write it, P before equals P after. Okay, so if you see a constant or a conservation of momentum question, make sure you write something down like this, because typically that is a point, because that is what they're testing you on. All right, so one thing to note, momentum is always conserved, right, in all the interactions. So we're going to talk about explosions and two types of collisions. Regardless of what's happening, momentum is always conserved, okay? And now for this particular topic, we're going to focus on what are called explosions. So for an explosion, right, typically nothing is moving at the beginning, so like a cannon. And after something happens, remember in the first video, we talked about how there's internal forces that cause objects to move. It could be, a cannon firing, it could be two people pushing off of each other. But what happens is typically nothing is moving before. So the total momentum of the system will be 0. And then you have the two objects, right, moving afterwards. And so what happens is, and let's say we're going to find the final velocity of the second object. Well, what happens is you get m1 v after 1 times, or divided by m2. Now, a couple things to note, right? That negative sign, well, what happens is if VA1 is designated as your positive, that means VA2 would go off in the other direction, okay? And so like, let's say we fire this cannon. Well, what happens? The cannonball goes out to the right, and what does the cannon do? It actually goes backwards, okay? And this is why cannons get put on wheels, because before, if they weren't on wheels, well, all that energy transfer and such would cause the cannon itself to go up, and therefore you got people scrambling in behind it so they don't get hit by this big cast iron object. So what do? They put them on wheels. Nowadays, with modern cannon technology, it's the barrel that actually recoils. And this is all we call it recoil speed when we talk about in terms of ballistics. But it could also be just simply two people pushing off on each other. All right, so let's look at an example problem. So you have a woman of mass 60 kilograms steps out of a canoe that has a mass of 40 kilograms. And if she steps out of the speed at 2 meters a second, at what speed does the canoe recoil? And then show that the velocity of the center of mass before and after are equal. Okay, so we got to do two things. One, we got to figure out how fast the canoe recoils with. So if she steps this way, the canoe is going to go backwards. So we know this is conservation momentum. So I definitely want to write that down. I know before the total momentum is 0, and we end up with, and sometimes, when doing problems, we go with like object A, object B. You can write the canoe and the woman, but a lot of times we'll just use letters or numbers. Okay, so again, following these steps, if I want maximum points, and we know that the velocity, and we did this solving on the previous slide, right? So we're going to have negative m1 VA1 over m2. And so we just simply plug in. She is 60, right? She steps out at 2 meters per second, and the canoe is 40. And so therefore, the canoe will recoil at negative 3 meters per second. And does this make sense? Yes, because the canoe is smaller in terms of mass, so it should go faster. Okay. Now we want to look at we want to show the velocity of the center of mass before and after equal. So the velocity of center of mass before, easy, 0, right? Because nothing was moving. So now what we need to do is use our velocity, the center of mass equation for after. So m1 vi, mi vi plus total mass, or divided by total mass. And so we have 60 times 2 plus 40 times negative 3 divided by 100. Now, don't forget your negative sign, because remember, the canoe recoils, so it goes backwards. And here we go. So 60 times 2 is 120, 40 times 3 is 120, but that's negative, so you get 120 minus 120 over 100. Well, right, the before and after velocity of the system is 0 meters per second. All right, so in the last video here, we're going to wrap up talking about conservation momentum and talk about 2 types of collisions.